recording. Were there any comments, questions, or concerns, ladies and gentlemen, regarding any of the homework that I gave you yesterday?
I found the setup a little bit interesting for the last question. That's it.
Okay, anybody? Going once, twice, thrice. Sold. Okay, cool. So if there was no questions, I mean, I think it's relatively straightforward. It's one equation, Q equals MC delta T, and away you go from there. So the last, we're going to end this. This is the last lesson in this chapter. And if you flip a couple more pages, you'll see that I have included review in here. So happy for you. Jasmine. Bring it back, Jasmine. Manuel. So bring it back. Your focus. You weren't for a second there. We're going to connect to thermal energy from power sources because what good does it to say we need just over 250,000 joules of energy to heat something? Okay, Tristan, no. 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 He was waiting for someone to throw food in his mouth from across the class. No. No. No, Manuel, do not throw that fry at Tristan. Thermal energy from power sources. Here we go. We know, Manuel, that we can change, Tristan, the temperature of an object according to the following equation. The one we did yesterday. Q equals MC delta T, where Q is thermal energy specifically. I could just call that big E and just call it energy, but it's in this case it's a specific type of energy. We call it Q. Q is just thermal energy. And to do this, energy has to come from somewhere. We have to provide it. One way to provide this energy is by slapping, like we saw yesterday with the chicken, the poultry pulverizer, whatever they called it. Another more reasonable way to do this is to use like an element or a hot plate or a stove or whatever. This question we're going to look at a microwave. So I have two. You want to get two going at once?
Oh, one is good enough.
Okay, this is the good one. And you can cut it like that.
Oh, really? Thank you.
It goes in the front.
Yeah, here?
Yeah.
Yeah, see there.
Yeah. You know how to do that, right? So I had students put in the open end into the thing. That's how I lost the last one.
We got it.
Okay, so no worries. Thank you. One way to provide energy is kettle, hot plate, etc. Another way to do it, microwave. So microwaves are all given wattages. That microwave at the back, if I'm not mistaken, is actually a 1200 watt microwave. It's pretty lame. It requires like 3 minutes to heat up my pasta for lunch. For my microwave at home, it is much bigger. It does it a lot faster. 1 watt. Do we remember what a watt represents? No. Yes, that's true. 700. No, that's the other way around. 1 horsepower. Yeah, yeah. But what is a watt? Like, what does a watt represent? Not just energy. It's work over time. Yeah. So the units that we originally gave, that we replaced with to give us a watt, were what? Work is measured in what units? Time is measured in? So 1 watt is equal to 1 joule per second. This means that a microwave, this microwave, the 1200 watt microwave, is providing 1200 joules of energy every second. Now you've got some context for, what are you wearing, Cohen? That's cool. You know what? Let's rock that. To give you this gives you now some context. 1200 joules every second. So if I wanted to heat the water in the question yesterday using this microwave, we're able to figure that out. We needed to provide 352,800 joules of energy to increase the temperature of 1.4 kilograms of water, which is just over 6 cups, from 18 degrees Celsius to 78 degrees Celsius. That's this question down here that I'm looking at. In this microwave, how long would that take? Well, I'm just looking at all of you kind of slowly. It started with you because you're like right there. How long would it take for that microwave to provide 352,800 joules of energy? Well, to figure that out, we know we've got wattage is a joule per second. So to divide joules by joules per second is going to give us a number of seconds. So to figure that out, all we have to do is take this and divide it by 1200, which is going to give us how many seconds?
293.3 repeater.
Which is how many minutes?
Hold up, give me a second. I got this. 4.89 minutes. 12 minutes.
So almost 5 minutes.
Yeah.
Hello, sir. Okay, go for it. Mr. Japatsky has almost all of them at this point. You ran out again. Okay. Okay. He's selling them. That's a great question. I'll ask Shapansky later. So 1200 joules every second. If you turn the microwave on for 1 second, how much energy are you giving your food? 1200 joules. If I turn it on for 2 seconds, we've given it 2400 joules. 30 seconds is just going to be 3 times 1200, 30 rather, times 1200, which is going to be 36,000 joules of energy. Just to now give you practical meaning. Did you leave that door open? No, the doors were shut. What a guy.
What a guy.
So, what happens though if you don't microwave it on, Tristan, where you go? Okay. What happens if you don't microwave on high though? What if you choose to put it on power level 8? Connor.
There'll be a difference in joules in its output.
What do you think power level 8 represents on a microwave? Kind of, not quite intensity. A microwave base power is power level 10. Means we're giving all of the power. If I put it down to power level 8,
Max out 10 is the 20%.
excuse me, less power. Specifically, how much less power?
20% less.
20% less power. So power level 8 on a microwave means we're using 80% of the power. Now, why would someone want to do something like this? Yeah.
If something burns really quick, then it just kind of gets it quick more.
Why wouldn't I just use less time on the microwave then?
Because its intensity is too quick to show the heat. I don't know.
But
Some things can't change the temperature too quick, so you need to change it like slowly, so the thing, I don't know,
no, you're absolutely right. Between what Luis said and what Tristan said, you guys are absolutely right. The reason we would use a lower power setting is because we might want to provide the same number of joules. We just might want to do it over a lower period of time. So Luis, the example he gave was, well, what if we have something that we need to heat it slower to give the heat time to dissipate through our object? That's a great reason to use less power for a longer time. Tristan, you said, what was it you who said burn the outside but the inside's still cold? Same kind of idea. So if you have a microwave on power level 8, then the power level is just going to be 80% of what it could have been. This 1200 watt microwave, or times 0.8, same thing as subtracting 20%, is going to be how much power? Are we cool with 80% being 0.8? Like that's not something I have to explain? That's something I have to explain to my nines. Yep. 960 watts. Cool. So what we're going to do here is we're going to rejig some formulas. We know, let's see what formulas we were given here. We had this formula here. Power equals work over time, which we can rejig to give us work equals power times time. Well, the amount of work you do on something, what are you giving the thing that you're doing work on? What are you giving to the thing you are doing work on? Energy. Thank you. So I can rewrite this as energy, the amount of energy we've given, is equal to the amount of power times the length of time. This formula is actually right here on your formula sheet. E equals PT. Comes from this formula here. P equals W over T. So we can combine now this formula combined with Q equals MC delta T. That's not correct. That's big T. Sorry. Little t is time, big T is temperature. Gives us the following formula. PT equals MC delta big T. But power can also be used to can also be determined by this formula here, which we've already seen. So this one here is not on your formula sheet. I am not going to add it to your formula sheet. You just need to understand that we can combine, because both of these pieces are here already. We're just combining this piece here with this piece here, recognizing that the energy that we're giving is heat energy. Cool? Comments, questions, concerns? So let's actually apply this stuff. A 600 watt kettle. Now, where is my kettle? This kettle is to put this into perspective, this is a 1500 watt kettle. This guy here. So the one that's listed there is a 600 watt kettle. Let's check my other one. Do not submerge. Pro tip right there. Oh, this is a 1000 watt kettle. So this one's 1500, this is 1000, so a 600 watt kettle is worse. Smaller than either of these two. Just to put that into some context for you. A 600 watt kettle is used for 3 minutes. If you're heating 1.5 kilograms of water, which again, to put this in perspective, is 1.5 liters of water. This is 6.5, 7 cups of water approximately. What's the change in temperature? Yeah, we're going to have to convert a bunch of stuff here. Well, first of all, do we want to, this 3 is minutes, not seconds. Time always needs to be measured in seconds. So 3 minutes, first of all, is going to be how many seconds? It's going to be 180 seconds. So if I want, what we're going to end up doing here, we're looking for delta T. So we're going to need this formula here, and we're going to need to find out, all it says is what is the change in temperature. Doesn't care what the starting temperature is, so we're not looking for a final temperature, we just want to know what the change is. Q equals MC delta T. This heat energy is going to be provided by this kettle. So we're going to use E equals PT to figure out how much energy is actually being produced over those 3 minutes. To figure, and assuming that all of it is in the form of heat, which it should be because my kettle doesn't produce like music or anything while it's playing. There's some light though, but we'll assume that the light's not a part of it. all of this energy is going to get converted into this energy. So I can combine these two into PT equals MC delta big T, and I can just fill it in. So the power is 600 watts. The time is 180 seconds. The mass of the water is 1.5 kilograms. The specific heat capacity of water is, if you haven't memorized it yet, you're gonna eventually because you'll use it a whole bunch of times. 4,200 times the change in temperature. What is the change in temperature over those 3 minutes? We can actually do a pretty interesting experiment here. Do I still have that scale? I totally do. Well, you guys are figuring that out. We're going to actually do this to see how accurate this is. Yep. 17.14 degrees. So not a lot.
Yeah, it's the same thing.
Okay, so here's what we're going to do. We are going to, here's what I want you to do. Where are we going to do it? We're going to, off to the side here, I'm hoping you have some space. What did I say the wattage was on this side? 1,500?
1,500 or 1,000.
This one's 1,500 and this is the one that we're going to use. Okay? I want you to tell me how long it's going to take my 1,500 watt kettle to heat 1.7 kilograms of water. We'll see how accurate we get that. That's the 1,500, yeah. Actually, no, we'll go for 1 kilogram. Let's do a liter. 1 kilogram of water.
Hang on, but what's the change in temperature? What? Is it like a degree or what?
No, it's a boil, I'm guessing. Yeah, but what's the starting temperature? Or we try to get it to the same temperature as this one.
Tap water.
Okay.
What are the
Is that
temperatures?
cold?
What's
What
the
temperature is
change
that?
in
Someone run, it's not room temperature. Someone run up to the lab. The table I had at the back, we'll send Tristan. Tristan, you like to run places.
I'll go Tristan.
You go Tristan in case he gets lost?
That's a serious issue.
Okay, so Tristan, you have the table at the back where we had all the equipment yesterday? No, were you present for that? Oh no, you weren't present for that, were you? Okay, one of those cans is a thermometer in it. Look at the thermometer.
And we're heating it to boiling point.
And it's, yes, it's going to be heated to boiling, which is 100 degrees.
So 100 minus unknown quantity or number.
I'm gonna get lost.
You can take James.
1,500.
He said no, right?
I said James.
1,500 T equals 1 for 200. Yeah, you don't have to. Well, I mean, the lab is going to make it up. Okay, well, that's what I'm telling you.
Zero this thing. There's nothing on the scale for that.
Are its contact points on the directly on the metal plate?
Too heavy? Too heavy. That says error. You've got to be kidding me.
Oh, correct.
It's the
Alright, 1001.
The other one.
It would be still heavy because there's water in there.
No, no, all I, that is true. How are you doing this in practice?
Like 14
You're right. Why did you have to be right?
What? Sorry?
No, you're fine. Let's do this a different way. Here's what we're gonna do. Big brain moment right here. No, that's not gonna work. Worst brain moment. Dang it.
You got this.
Okay.
We will help you.
Yes, we need the temperature of the water. I gotta figure out. I was also like this.
Some question like delta T is the temperature.
Delta T is the change in temperature. So now you're gonna tell us what the temperature is here in a bit. If you could hold it right there. And tell us when to stop the meter. I need to figure out a way to actually measure how much water we have.
No.
How long does it take?
Yeah, I understand.
So you have this triangle, right? So this side is,
They're like,
oh, okay, so that's 11, right? So you can't change the length of this one. You don't know what this is, right? So technically, you could open it up like most people do.
right, and that's where you're showing like the degrees and then find the closest.
That's for the 90-degree one.
Okay.
That's to see if it can even work.
But how do you place this?
Place what?
Where you figure out, do you place it on the 90 degree?
Well, like, are you asking, like, to see if a line can work?
No, I just wanna know how to
Set what up?
the line, figure out what the line that I
Well, it can be
draw
two
is right
different
here.
To make it a 90 degree. So basically, you have a triangle, right? Say you got that, right? I don't know. Unknown. This is 8. This is 4. Right? Let's say, like you have a okay, I don't know how to explain it. So, let's say, this is the shortest distance right here, right? So what he's saying is, if this line here is less than 3, or less than 4, this triangle doesn't work.
Okay, I get that
Because
part.
that's a longer,
Yeah, I get that. Because each side has to,
yeah.
well, this has to be towards this and so on, all that around. But I get the part where it's like, okay, well, if it's like, I think it's just not long, it's take 5.5 to the very closest point.
Okay, so what he did was, he had that time.
You told me in class that you made up about
30 degrees.
I don't get how you did what you're saying.
Okay, look.
That wasn't about,
So we have a 30 degree, right? So we look at it like this. Okay, so 30 degree, let's say this is
you said about.
11. Okay, and then this is like 15. He wants to, because we know how to do right triangles, right? So if we want this here, we use this number and this number, right? To find what this would be if it was a 90-degree angle. Yeah, so let's say this number came out to be 10, then this can't be 11 because the shortest, or sorry, if this number came out to be over 11, then this wouldn't work, right? Because that is more than this.
Hence, this triangle doesn't exist.
Do you understand?
I get that. Now, how does this one work where we don't, where it's not
Where
right?
it's shorter or longer?
Yeah, and it's not a right triangle.
First of all, why do you have a curved edge?
Yeah, I didn't go.
That's not a triangle. So you have like this, or let me,
Okay, Naya, what's the temperature?
something like that.
30 degrees.
30 degrees.
Yeah, well, it's like just under.
Yeah,
It's not Fahrenheit, is it?
and then Connor. He said, you knew this angle.
Pulling that 29 and a half. Okay, cool. There you
You
go.
knew what like, you knew this and this one. So 6 and 11.
That one works?
Okay, yes, this one works. This one goes up to 5 kilograms.
So
Okay, so bringing it back, we have
one like or the other. Because that one length is still no. You could extend it to this one.
And that's what I'm saying with this guy here.
Yeah.
Sorry, what'd you say? The water temperature was what?
29.5 degrees. Let's do the whole thing.
Wait, are you doing a kilogram of water or not?
Okay, so we are doing 1,093 grams of water.
Come on.
1,093 grams. 1.093 kilos.
Is this the 1500 can?
This is the 1,500 can.
1.093 kilograms.
1.093, yeah. The initial temperature, according to Dia, was 29.5 degrees. 29.5 degrees, and we're going to bring this thing to boiling.
How many grams did you have? 100 degrees Celsius.
Boiling, thank you. Boiling is at 100 degrees Celsius.
What
There
was
is
the last-
1,093 grams.
1093.
1,093.
And kilo.
Okay. We're taking it from 29.5 degrees to boiling.
So it's 100, yeah.
How long should this take?
Hold up.
So
Nobody said nothing.
15 watt.
So it's going to be like 100 minus 25, and that's
That's final minus initial, yeah?
okay.
Let me know when you've got a number and we'll start. And while we're waiting, we can do some more of these questions. Two minutes, 15 seconds. Okay. Or is that 250 seconds? 215 seconds. So how put that into minutes and seconds for me?
3.6 seconds. 3.6.
So what's 0.6 minutes back into seconds?
270.
That's not minutes, that's seconds.
Three. So what's 0.6 back into seconds? 0.6 times 60? 36? So 3 minutes, 36 seconds. That's what you're suggesting, okay?
Mr. Rudolph,
Here we go.
how old's the kettle?
Couple years. We'll find
Can
out
we
how.
consider that it wears a little bit?
No.
And doesn't have...
Done. I turned it on and time has started.
Oh, come on.
So, what you're the math that you guys did suggested that this thing should take how much time? 3 minutes and 36 seconds. There we go. While we're waiting, we'll see how good the kettle actually is. Another example. Instead of using a kettle, we're now going to try and heat water with a hot plate. The hot plate has a power of 800 watts, but since our pot doesn't cover the whole surface, only 60% of that power is actually being used to heat the water.
Okay, I know what to do.
So how much power is actually being used? And then if we're heating 1.5 kilograms for 3 minutes, how is that going to increase the temperature?
Well, we're only using 480 watts, so
So we're using 60% of the 800. So that's going to give us, Connor already said it, 480 watts. So power times time equals mass times specific heat capacity times change in temperature. Let me know what you get.
okay, I see. Right here.
We just broke 2 minutes. Okay. 2 minutes, 15 seconds. Okay. What's the temperature change now if we're using a 800 watt hot plate that's 60% efficient? 13.7. Love it. Degrees Celsius. Another way to do this exact kind of problem is instead of putting the water in an object and then putting it on a kettle or a hot plate, is to heat an object by adding something hot to it and allowing the conduction to transfer the heat. So imagine we have a cool glass of water and we add a boiling piece of hot metal to it. What's going to happen?
The water is going to boil after that period of time.
Do we know the water is going to boil?
Or the metal is going to like
So I've got my water in a container. I add my hot piece of metal to it.
because in my head, like you would put the metal, the water is going to boil, not out of the water, like only a small piece of water is going to boil, and after the metal is going to get colder and reach the same temperature that.
So what I'm hearing you say, Luis, is the energy from the hot object is going to disperse heat out into the water. You say it's initially going to boil. Well, you might have some steam produced at the beginning. Is the whole thing going to boil? We don't know. But you said at the end you're going to have something where the metal and the water are at the same temperature. Water's going to get warmer. What are we at?
4 minutes and 5 seconds.
4 minutes, 5 seconds, so we're over.
Why didn't you make the temperature stopwatch?
It is a timer. Sorry, what?
Use the stopwatch as a timer.
I used the stopwatch to figure out how much time it actually takes.
Oh, does it whistle?
It'll shut off when it's at 100 degrees. Which means the kettle is not operating at 1500 watts.
Exactly. It's
So we can actually figure out what the wattage of the kettle actually is.
worn down to kettle's not what it used to be.
There we go, I know what I'm saying. Yeah, and we're just maybe then we'll look at it holder shuts off, yeah. Done.
Okay, so we can actually work backwards. That was 4 minutes and 49 seconds. So we can work backwards and figure out what the wattage actually is of that kettle. Okay, so back to this. We'll do that in a second.
Oh, come on.
Back to this. What's going to happen here is the metal, as Luis already said, gives thermal energy to the water.
What was it, 4 minutes or what?
What does it say? 4 minutes and
49 seconds.
49 seconds. Until, Luis already said it, they are the same temperature. They are the same temp. And the language that we use to describe that, I think I already said it last class, but the idea is that they're at thermal equilibrium. Their two objects are at the same temperature. So flip the page when you're ready. The general method for dealing with mixtures like this is to talk about the heat or the thermal energy lost by one object plus the thermal energy gained by the other object. And those two should be equal and opposite, which means when you sum them, they should add to 0. Where Q, as before, is mc delta T. And we are assuming that no energy is being lost to the surroundings. So, for example, let's assume I have a 0.06 kilogram block of aluminum. That's 60 grams, not very big, not very small either. 60 grams of aluminum at 90 degrees Celsius. We're adding it to 0.09 kilograms of water at 20 degrees Celsius. What's going to be the final temperature of those two objects when all is said and done? So we know the aluminum is going to be the thing losing energy. The water is going to be gaining energy. So we're going to Q aluminum plus the Q for my water is going to equal 0, assuming that nothing was lost anywhere else. So this is going to be mc delta T plus mc delta T equals 0. And now we can start to fill this thing in for both aluminum and water. The mass of my aluminum is 0.06 kilograms. What is the specific heat capacity of aluminum? Sorry, 920. And delta T is temperature final minus temperature initial. Temperature final we don't know. That's what we're looking for. The original temperature of my aluminum was 90 degrees. Plus the mass of my water times the specific heat capacity of water is going to equal, or times rather, the final temperature of my water. And the beauty here is these T finals are both the same at thermal equilibrium minus the initial temperature of my water is going to equal 0. So I did some of the math already. So I'm going to either figure it, by all means attempt to figure it out on your own, but I'm going to give you some more here. 0.06 times 920 is 55.2, so it's going to be 55.2 T final minus 90 plus 378 T final minus 20 equals 0. I'm going to distribute those values in. So I'm going to get 55.2 T final minus 4,968 plus 378 T final minus 20. 7,560 equals 0. So I'm going to get 433.2 T final equals 12528. So my final temperature. Did you guys got an answer already? Some of you? Yep.
28.92.
28.92 degrees Celsius. So that 60 grams of aluminum at 90 degrees Celsius was only able to raise the temperature of the water almost 9 degrees. Interesting. Questions, comments, concerns about this?
Can we go back and calculate water temperature?
The wattage of the thing.
It's gonna bother me.
I want to do one more example here.
Oh, come on, man.
You found it? 1200? Which means it's either only 80% efficient, or we could have been off with my, I could have been off with my mass. Nia's temperature, I was good. Or it's only 80% efficient. Okay. A new metal is discovered. We want to determine its specific heat capacity. In order to do this, what we're going to do is we're going to heat 100 grams of the metal to 100 degrees Celsius and then drop it in 1.1 kilograms of water at 20 degrees Celsius and measure the final temperature. We measure the final temperature to be 28 degrees Celsius. What is the specific heat capacity of that metal? So it's the same setup. We've got the Q for our metal plus the Q for our water. It's going to equal 0. So we have MC delta T plus MC delta T equals 0. The mass of the metal is 0.1 kilograms. Specific heat capacity is what we're looking for. We know the change in temperature. It was 100, now it's 28. Sorry, so it's going to be final was 28 minus 100 plus the mass of our water, 1.1 kilograms, times 4,200, the specific heat capacity for that water, times the change in temperature of the water. Final was 28 and initial was 20. What is the specific heat capacity of that metal? I am content to wait. If anyone wants to see the algebra, let me know. Okay, what'd you get?
5,133.3 repeater. That's all right.
Units?
What he said.
Joules per kilogram per degree Celsius. That's what I got. Does anyone want to see the algebra, or are we good? Okay. That's it. So now, two things that we've done today. We've connected power transfer from like a electronic heating object, and we've connected this idea of mixing things of different temperatures and seeing what happens there. So there's a whole bunch of applications to this, but I'll let you play with it. So your homework for today is this. The review.
Or just this whole page.
This is, how come this is different? Well, that one's the same, that one's the
Oh, no,
same,
this
that
is
one's the
the-
same, that one's the same.
How about you say some?
Oh, this is different. I don't like this.
Okay.
I'm sorry. I'm gonna let me photocopy something. This is not your homework. I put the wrong one in there. This one is going to be your homework.
Cool. I'm good with that.
Can I go to the washroom?
You may go to the washroom, yes. Walk in real quick here.
This is fun though. No, like going and using the classroom. Yeah. Yeah, see? Especially do it. Nah, man. I think it'd be cool initially and then, dude. I wish I could go back though, but your school would just be sparking off. Oh my gosh. I wouldn't be allowed to play. I hit Prince too hard with dodgeballs and all my football. I'm not gonna be any different. I was just gonna have to like do that. I can't do that. Oh yeah. I'd always do something like super ball. Who's everybody missing that? Who's so lucky. You're gonna be an elementary school teacher. You gotta drive. I know, but you gotta drive. So fun. We don't have any homework. Why you work? That's just not a choice. Has anybody got some lotion?
Just let your kids drive.
Like that. I did that before. It wasn't so good. I like it.
Okay, this is what you guys are doing for homework.
Why?
If you want to
Come grab one.
remember this
Don't have to.
Can you pass me one, Mr. Rudolph?
Right there, yeah. Up here. Yeah.
Oh, it's fresh off the press. Here you go.
You may.
I might have gone to the big one too.
That is what I want you guys to do for homework. So this was the last chapter that we're going to do, or the last unit, sorry, of the chapter that we're going to do. So you guys are going to get a couple days. On Monday, I'll give you guys we have the review, but Monday, Tuesday, I will give us time to review. Right, you have and come on. Test is going to be on Wednesday next week. Wednesday next week is going to be our chapter test on
time.
work energy. Yes, so it's a regular night block. He's going to double block Tuesday.
Yeah, but most of the tests that you've given us,
You have to write it
we
on
needed like a double
Tuesday or
block
Thursday.
or a lunch block right before it. Will this be a really long?
You can either go into lunch.
Wednesday morning, guys, ladies and gentlemen, Wednesday, you have physics first block. So you can come a little early on Wednesday, or alternatively, in D block, I have my prep. So you can just keep writing because no one's coming here. But then you're going to end up being late for your next class. Sorry? So you guys are writing this chapter. This is going to be Wednesday, first block. You'll get Monday to review for sure, possibly Tuesday. Probably Tuesday, it's a short block. Maybe Monday, Tuesday to review. Cool?
Is there gonna be like a mock section?
Always.
That is my standard format for physics tests. People usually do. Multiple choice is largely theoretical, and for some reason it's
It makes
so again, there's still almost 10 minutes left. Use this time, guys. Don't just do nothing. Gentlemen on the side, you start doing this stuff. That is the homework. Yes, that's it.
So we don't do any exchange.
Some of the questions there are up to 4. I think they're the same, but I took off the last question and added a couple other ones on my old sheet. I want you to do this one instead of the one that's in there.
Oh, we definitely don't do anything after the big paper that says review, right?
That we're gonna work. I'm gonna give you time to do that Monday, Tuesday.
Okay. That's good.
Just the piece of paper you grabbed here. That is your homework.